Hi everyone, welcome to Snetly. In today's video, we will discuss about the closed loop speed control of 3-phase induction motor drive with a PI control logic. Here we will implement both model level design as well as hardware implementation. First we will go with the hardware connections and then we will see the model level design to run the motor in closed loop. This is the hardware unit of our Snetly where we will connect our digital input and digital output and the analog signals. And here this is a normal 3-phase voltage source inverter module to run the induction motor, and here we are using 0.5 HP 3-phase induction motor, and to run the motor we are going to use the auto transformer for the DC bus link for the voltage source inverter. This is the hardware component required to run the motor in closed loop. In previous video we have seen the open loop speed control of induction motor drive. Firstly we will go with the open loop, then small change in the model level design for the closed loop control. From the encoder we will get the digital input. Based on the digital input we are going to measure the speed of the motor with the help of pulse to speed block. Just we need to know the pulse per revolution of your encoder. Here our encoder is 625 ppr, so we will connect and configure the values. In DB9 connector we will connect the digital input from the encoder. So we connected two signal from the encoder, A signal and B signal, both are 625 ppr. So you can use any one of the signal to measure the speed. The pulses will be calculated to the RPM, revolution per minute. Just we need to configure number of ppr of particular encoder which we are using in our application. And secondly, we need to compare our 3 reference signal with a carrier signal in order to generate a sine PWM. Here I am using one knob as well as constant just for the multiplication factor of your amplitude and frequency. Since we are going for the VBF control technique, I am going variable of amplitude as well as frequency control. Inside the processor we have already seen we are generating a 3 reference signal RYB with a phase shift of plus 120 and minus 120. This block I have already shown in the open loop speed control. Same block we are going for using. After creating the block inside the processor, just build and back to schematic. From the processor we will get the 3 reference signal with a phase shift of 120 degree. The waveform has been connected to the DSO for viewing the sine reference signal. From the math block we will get the frequency output as well as amplitude output, which has been connected to D0 and D1 input. Here for carrier signal I am using the triangle. To configure the value, just right click the block. Here we are going for the minimum and maximum value minus 1 to plus 1, and the triangle switching frequency 7500, 7.5 kilohertz. Just click on the apply register to save the configuration values. Now we need to compare the reference signal with the carrier signal, so we require a comparator block. From the comparator block we will get 6 digital output. In order to configure with the hardware unit, we require a dead time for the semiconductor switches. So here we are using this dead time around 1 microsecond. The values of dead time will be changes based on the hardware switches used in the applications. The output of dead time will be directly connected to the digital output pin of Snetly module in the DB25 connector. And finally we are going for the analog signal, where we will measure the 3-phase current waveform of the motor. Here you can measure your voltage signal as well as current signal, even if you have any torque sensor or position sensors or temperature sensor. Based on the feedback values, might be your analog value from 0 to 10 volt or some other ranges, you can select based on. Here we have 4 ranges, 4 to 20 milliamps, 20 ampere for current sensor, and 0 to 20 volt for our voltage, as well as 0 to 750 volt. All are bipolars. In the hardware unit of Snetly, we need to connect the encoder input to digital input point area DB9 connector. From the encoder, we will get 5 cables plus 5 volt, ground and 2 signals. Then from the Snetly, we will get the digital output to run the 3-phase voltage source inverter module. Totally we will get 6 digital output from this Snetly, which has been connected to the voltage source inverter. From the inverter we will get RYB output. We need to connect to the motor terminal, and for the running the drive we need a source. So from the auto transformer I am going to connect single phase. The maximum DC link for this drive is around 300 volt DC link. From the auto transformer it will connect to the input to the drive. So by just varying the auto transformer output, you can vary your DC bus link. And here we are measuring the 3-phase current waveform of your induction motor. So connect to the sensor signal area, nothing but your analog signal. After clicking, just click on the run button. By varying the auto transformer to maximum DC link of particular voltage source inverter module you are using, here we are going for maximum 300 volt DC. Once motor starts rotate, we will get the feedback from the encoder slowly based on the speed of motor rotate. As well as you can see the RPM of motor in the display. By simply varying the knob of, we will get the variation in amplitude as well as frequency of your reference signal, so that the modulation index of sine PWM will be changed. Based on that we will get a respective voltage around the voltage source inverter module. Then the motor starts rotate. Once the motor starts rotate, you can observe the current waveform in analog signal area. By keeping the maximum value of your modulation index, maximum RPM will be running, as well as you can observe your sine PWM output, digital output, and your current waveform. For measurement of speed, you can either go with numerical or with scope value. Here plotter has been used for the measurement of speed. Now the application has been running on the real time. We can observe here encoder signal as well as the speed of motor and your reference signal and the current waveform of your particular application we are using. Here we are using 3-phase induction motor drive, so our reference signal will be sinusoidal. So the waveform we are getting in the analog signal is sine. Majorly we have done 3 steps, one for the measurement of speed, and second will be PWM generation, and third for the current measurement. If you want to measure your voltage signal, you can connect those also, which will be seen in the later videos. We will show the voltage signal as well as some other torque sensor or position sensor feedback, either temperature sensor. the respective sensor we can connect to the Snetly module with the respective range of voltage. In open loop condition, we need to apply the load to the maximum rated of motor. Here the maximum rated is 1 ampere for the motor. By applying the load, the speed of motor gradually decreases in open loop cases, which you can observe in the display value. By applying load to the motor RPM slowly decreasing. This is the complete model for designing the motor to run in an open loop condition for 3-phase induction motor drive with VBF control logic. Here we are going to change some modification for the closed loop speed control. Let me stop the system and we will change the required block to be changing for the closed loop control. Here we are going for the PI control logic. Firstly, I am removing the knob. In previous open loop cases, we have used a knob for the variation of amplitude and frequency. Now here I am going to use knob as a set speed, minimum 250 to maximum 1350. And take your PID block. Right click over the PID block to configure the value. In PID we need to give the input, set speed and the measured speed, and we will get the output. Here we need to assign your Kp value and Ka value directly, which calculated from the theoretical concept, and your lower limit and upper limit, and for the sample time to commit the PID block. Just apply Kp value and Ki value, lower limit, upper limit. Here two set of PID is available. If you are going for any current control and voltage control, you can use two PID at a time. Now from the knob output I connected to the set speed, the actual speed measured from the pulse to speed block where we get the RPM of motor. The output of PID has been connected to the math block. In previous we have multiplied the knob value into constant, we will get the amplitude as well as frequency. Here based on the PID output, our reference signal amplitude as well as frequency will be varying. One more thing, if you want to take any waveform for your paper publishing, just you can take a mail from this system, click on the report desk. In report desk you can observe maximum 12 waveform at a time. Here we are going to just measure 3 waveform of current waveform of induction motor drive, which has been connected to the channel respectively. Whichever channel you are connected, just click here and drag it over there. Here we are connected to the 5th channel, 6th channel and 7th channel of DSO for the current measurement. So just click 5th and 6th, 7, and you can adjust your x-axis and y-axis value of your signals. In report desk, I am going to measure the current waveform of the motor, which we are connected to the analog output channel of 5th and 6th, 7th channel of DSO. So corresponding channel need to be given to the scope number 1. And here in the report desk, we can take a snap of the waveform through mail. And in the plotter, we are going to measure the set speed and actual speed. And this is the model required to run the motor in a closed loop speed control action. Only one block we have additionally changed. PID block. In open loop we are not using the PID block. Here we are going with the control logic of PI for the closed loop action. Similarly, there are different control technique for running the motor in closed loop. Here the knob has been used to vary the set speed from minimum 250 to maximum 1350. By adjusting the knob value, our set speed will be changed. Then the PID need to change the respective reference signal amplitude as well as frequency so that the corresponding output voltage of our voltage source inverter module should be increased and decreased so that the motor should attain the set speed value. In hardware configuration, the connections which we have already made for the open loop, same connections. We need to give a digital input from the encoder and digital output to the power module and motor terminal in series with your current sensor for the measurement of current, as well as you can connect your voltage feedback also. In next video we will show about the voltage waveforms also. Here in reporters you can observe your current waveform with a phase shift of 120 degree. In reporters you can change the channel colors as well as you can naming your channel name. Here I have kept the set speed is 250 and actual speed also showing is 250, and the corresponding waveform reference signal amplitude and frequency you can observe in the DSO. It is also linearly changing based on the set speed. And correspondingly you can observe your motor speed has been rotating to the set speed value. In analog input we have connected the 3 current signal measurement so that you can observe the waveform of your current waveform sinusoidal with a phase shift of 120 degrees shown in the DSO. In open loop condition, when we are applying load to the motor, the speed of the motor has been reduced gradually, but in a closed loop we are going to apply the same load to the motor, but our set speed and actual speed should be matched. Here the maximum load we are going for the motor rated ampere around 1 ampere for the 0.5 HP motor. Similarly for other motor, the motor rated ampere will be changed so that we need to apply to the maximum rated ampere. In open loop condition, we have seen that the speed has been gradually decreased once we are applying the load, but in a closed loop, until the motor rated ampere, our set speed and actual speed should match the value. Here from the knob value you can observe that set speed has been 1121 and the actual speed is shown in the display. It is similar like the set speed value. The actual speed will be attained with the help of PI value. Once the PI value changes, our reference signal amplitude and frequency will change. Based on that, our modulation index will be changing. So the corresponding speed will be attained with the help of corresponding output voltage from the voltage source inverter module. Here we have seen the complete module level design for the real-time implementation of induction motor in a closed loop with a PI control logic. In previous video we have seen the open loop control in a VBF technique. Here also we are seeing the VBF technique with the PI control logic. That's all for today's video. Thanks for watching.